Somewhere in the late 1990s, a physicist named James Gates, working on a branch of theoretical physics called supersymmetry, was deep inside the mathematics of string theory when he found something that stopped him. Buried within the equations describing the behavior of fundamental particles at the deepest level of physical reality, he found a specific type of error-correcting code. Not a metaphor, not a loose analogy. An actual, formally recognizable class of self-dual linear binary codes, the same family of codes used in browser software to detect and correct errors in data transmission across the internet. He has described this finding in multiple public lectures and interviews since, including a 2012 presentation that circulated widely, noting, with characteristic understatement, that he doesn't know what to make of it, that it might mean nothing, and that it might mean something deeply strange about the nature of physical reality. No fraudulent AI revelation produced this finding. It came from decades of rigorous mathematical physics applied to some of the most fundamental equations describing how the universe behaves at the smallest scales. And it sits, quietly and uncomfortably, alongside a growing body of serious scientific and philosophical argument that the question of whether the universe we inhabit is, in some technical sense, a computational simulation isn't a fringe idea. It might be one of the most important questions in the history of human thought. The simulation hypothesis, as it's now formally known in philosophical and scientific literature, has a specific, rigorous modern origin that's worth understanding precisely because it's so often confused with vaguer, older ideas about reality being an illusion. The modern version isn't a spiritual or mystical claim. It's a probability argument, and it was formalized in 2003 by Swedish philosopher Nick Bostrom in a paper published in the Philosophical Quarterly titled, "Are You Living in a Computer Simulation?", which has since become one of the most cited and discussed papers in contemporary philosophy of mind and metaphysics, read and engaged with by physicists, computer scientists, and mathematicians, well outside its original philosophical audience. Bostrom's argument is built around what he calls a trilemma, 3 possible propositions, at least one of which he argues must be true, with the specific one that turns out to be true having dramatically different implications for how we understand our situation. The first proposition is that virtually all civilizations at roughly our current level of technological development go extinct before they reach the computational capability to run detailed simulations of conscious minds and historical processes. The second is that virtually all technologically mature civilizations, ones that do reach that level of computational power, choose not to run such simulations for ethical, practical, or cultural reasons we can't fully anticipate from our current vantage point. The third, and the one that generates the most attention, is that if the first 2 propositions are both false, meaning civilizations do survive and do run ancestor simulations, then the number of simulated conscious minds in existence at any given moment would vastly, astronomically outnumber the biological ones, since a single technologically advanced civilization could potentially run enormous numbers of detailed simulations simultaneously, meaning the statistical probability that any given conscious mind, including yours, is one of the rare biological originals, rather than one of the vastly more numerous simulated ones, becomes extremely small. Bostrom himself has been careful to note that his argument doesn't tell you which of the 3 propositions is true. It simply establishes, through straightforward probability reasoning, that you're forced to accept one of them. If you believe human civilization has a reasonable chance of reaching advanced computational maturity and would actually choose to run detailed historical or consciousness simulations, you're almost logically compelled to assign a non-trivial probability to the possibility that you're already in one. He's also been explicit that the argument doesn't require the simulation to be running on anything resembling a conventional computer, and doesn't require the simulator to be anything resembling a human, only that some form of information processing substrate, capable of generating the relevant physical experience, exists somewhere in the causal history of what you experience as reality. What makes this more than a philosophical thought experiment, and what has drawn serious engagement from physicists and computer scientists rather than just philosophers, is a set of observations about the structure of physical reality that look, from certain angles, uncomfortably like the architecture of a computational system rather than what we'd naively expect from a purely continuous analog physical universe. Start with the most fundamental one. The universe appears to be quantized. At the smallest scales we can measure and probe, physical quantities don't vary continuously and smoothly the way an analog system would. They come in discrete packets, quanta. Energy doesn't flow in arbitrary amounts. It comes in specific minimum units described by Planck's constant. There's a minimum length, the Planck length at roughly 10 to the minus 35 meters, below which the concept of measurable distance appears to break down entirely within current physics. There's a maximum speed, the speed of light, functioning something like a hard processing limit on how fast information can propagate across the system. Physicists working entirely within conventional physics frameworks have their own explanations for why these quantization limits exist, rooted in quantum mechanics and general relativity. But it's mathematically notable that a quantized, speed-limited, discretized universe looks structurally similar, at least superficially, to a computational system operating under finite processing constraints. Exactly what you'd expect if physical reality were being generated by something with finite but very large computational resources. Then there's the measurement problem in quantum mechanics, probably the single most philosophically disturbing feature of established, experimentally confirmed physics, and one that has resisted fully satisfying explanation for a century despite the mathematical formalism describing it working with extraordinary precision. In quantum mechanics, particles don't have definite fixed properties until they're measured or otherwise interact with something. Before measurement, a particle exists in what's described as a superposition, a mathematical combination of multiple possible states simultaneously. The act of measurement causes the superposition to resolve into a single definite outcome, a process called wave function collapse, whose underlying mechanism remains one of the deepest unsettled questions in the foundations of physics. Several leading interpretations of quantum mechanics, including the Copenhagen interpretation and the more recent relational quantum mechanics, describe this in ways that place the act of observation or interaction, rather than any underlying objective state, at the center of what physical reality actually is. A universe that only fully resolves the definite properties of things when they're observed or measured looks, from one angle, like a universe conserving computational resources by not calculating the full detail of things nobody's currently looking at, an observation that physicists working within the simulation hypothesis framework have found worth taking seriously as at least a structural parallel worth examining, even without claiming it as definitive proof. The double-slit experiment, one of the most replicated experiments in the history of physics, makes this feature of quantum mechanics viscerally concrete. Fire individual photons or electrons through two parallel slits at a detector screen, one at a time, and an interference pattern builds up over time that can only be explained if each individual particle somehow passes through both slits simultaneously, interfering with itself. But put a detector at the slits to determine which one the particle actually goes through, and the interference pattern immediately disappears, replaced by a simple two-band pattern as if the particles were behaving like classical objects. The particle's behavior changes based on whether the information about which path it took is observable. This is not a theoretical prediction. It's a reproducible experimental result replicated in laboratories around the world for decades. The universe appears, at some fundamental level, to behave differently depending on what information is observable within it, a feature with no fully satisfying classical physical explanation after a century of trying, and one that philosophers of physics continue to actively debate. James Gates's error-correcting code finding, mentioned at the opening, fits into this broader picture in an interesting way. The specific codes he identified, called doubly even self-dual linear binary error-correcting codes, aren't just any mathematical structure. They're a class of code specifically designed to detect and correct errors in information transmission, ensuring that data remains accurate even in the presence of noise and interference. Finding this structure embedded within the equations of supersymmetry is either a profound coincidence, a consequence of some deep mathematical relationship between physics and information theory that we don't yet understand, or, as Gates himself has suggested as one possible interpretation, while explicitly not claiming it as a conclusion, something that might indicate information processing is more fundamental to physical reality than matter and energy. A possibility that theoretical physicists, including John Archibald Wheeler and, more recently, Max Tegmark, have argued for from entirely independent directions. Wheeler, one of the most influential physicists of the 20th century, spent much of his later career developing what he called the participatory universe, or it from bit, the idea that physical reality is fundamentally informational rather than material, that every physical quantity derives its existence from answers to yes or no questions, binary choices, observations, measurements. Tegmark, a cosmologist at MIT, has gone further, arguing in a fully developed theoretical framework, sometimes called the mathematical universe hypothesis, that physical reality doesn't merely resemble or follow mathematics, but actually is mathematical structure, that the universe is, in the most literal sense, a mathematical object, which would mean that the distinction between a real universe and a sufficiently complete mathematical simulation of a universe is not a meaningful distinction at all. These are not positions of scientific consensus, and it's important to be clear about that. The majority of working physicists do not endorse the simulation hypothesis as their preferred framework for understanding physical reality, and there are serious, substantive objections that deserve honest engagement alongside the arguments in its favor. The most significant computational objection comes from simply trying to estimate what it would actually take to simulate a universe with the fidelity we observe. Physicist Seth Lloyd, working at MIT, has calculated that simulating a single cubic centimeter of space to quantum mechanical precision for a single second would require more computational operations than the estimated total number of atoms in the observable universe, and our observable universe contains roughly 100 billion galaxies each, with roughly 100 billion stars, each surrounded by planets. Even granting extraordinary technological advancement over our current capabilities, the computational resources required to simulate the universe to the precision we actually experience, it would appear to be, on conservative estimates, staggeringly beyond any practical realization. Proponents of the simulation hypothesis respond that a sufficiently advanced simulator needn't compute everything at maximum fidelity simultaneously, only what's actually being observed or interacted with at any given moment, exactly the efficiency-conserving approach quantum measurement behavior seems to implement, but critics point out that this response assumes the answer rather than proving it. A related technical objection involves what's sometimes called the fine-tuning problem within the simulation framework. Our universe has roughly 26 fundamental physical constants, numbers like the strength of gravity, the mass of the electron, and the cosmological constant governing the expansion of the universe that appear to be tuned with extraordinary precision to values that allow complex structures like stars, planets, and ultimately conscious life to exist. Change most of these constants by even tiny fractions, and the universe becomes lifeless, either collapsing back into a point immediately after the Big Bang, or expanding so fast that matter never condenses into structures at all. Physicists have grappled with this fine-tuning for decades, proposing explanations ranging from the anthropic principle to the multiverse, and it's genuinely unsolved. Within the simulation hypothesis, fine-tuning has a simple but somewhat unsatisfying explanation. A simulator would logically choose constants compatible with the eventual development of interesting complex systems, since those would be the most computationally interesting things to run. But critics note that invoking a simulator to explain fine-tuning is essentially replacing one mystery with a larger one, requiring an external entity capable of choosing and implementing physical constants without any explanation of that entity's own origin or substrate. There's also a serious philosophical objection worth naming clearly, one that doesn't depend on computational power estimates at all. Even if you grant Bostrom's probability argument in full, it still doesn't tell you anything about what the simulation's substrate is, who or what is running it, or what their motivations might be. The simulation hypothesis is sometimes conflated with specific claims about the simulator's nature or intentions, claims that have no logical connection to the core argument. The trilemma establishes, at most, that we might be simulated. It says nothing about whether the simulator resembles anything in our experience, whether they're monitoring us, whether there's any purpose to the simulation, or whether the distinction between inside and outside the simulation is even coherent. These are points Bostrom himself has been explicit about in interviews, noting that the hypothesis is frequently overinterpreted in popular coverage. What's genuinely notable and worth understanding is how seriously figures at the frontier of physics and computer science have engaged with these questions in recent years, well beyond philosophical speculation. Elon Musk has made public statements suggesting he considers the probability of base reality quite low, though his reasoning has never been formally published. Neil deGrasse Tyson at a 2016 Isaac Asimov memorial debate specifically on the simulation hypothesis attended by several physicists and philosophers, stated he thinks the probability we're in a simulation is very high, a position he's clarified as reflecting the philosophical force of Bostrom's argument rather than any specific physical evidence. MIT cosmologist Max Tegmark, Columbia University physicist Brian Greene, and University of Washington physicist Andreas Karch have all engaged seriously and publicly with the simulation question in mainstream academic contexts, as has Oxford philosopher David Chalmers, one of the leading figures in consciousness research, who published a major book in 2022 specifically addressing the simulation hypothesis within the broader framework of philosophy of mind and the nature of reality. There have been actual experimental attempts to look for computational signatures in the structure of physical reality, the kind of signatures that might distinguish a simulated universe from a purely physical one. Two physicists, Silas Bean, Zorae Davudi, and Martin Savage, published a 2012 paper in the European Physical Journal proposing a specific, testable prediction. If the universe is being simulated on a computational lattice, meaning if space-time has a discrete underlying grid structure at some fundamental scale, this should produce a detectable cutoff in the energy spectrum of cosmic rays, the ultra-high energy particles arriving from outside the galaxy, specifically oriented relative to the axis of that underlying computational grid. This is a genuinely falsifiable prediction in principle. though detecting it would require sensitivity beyond current instruments. The proposal has been criticized by other physicists for making specific assumptions about the simulation's computational architecture that may not be warranted, but it represents a serious attempt to move the simulation hypothesis from purely philosophical argument towards something potentially empirically testable, a significant methodological advance regardless of whether the specific prediction turns out to be correct. What all of this amounts to, taken together, is one of the genuinely most interesting and unresolved questions at the intersection of physics, philosophy, computer science, and the study of consciousness, one that's been taken seriously by serious people for serious reasons while remaining far from settled in any direction. The arguments for taking the simulation hypothesis seriously include Bostrom's rigorous probability trilemma, the quantized and observer-dependent structure of quantum mechanics, the discovery of error-correcting code structures in supersymmetric physics, the eit from bit tradition in theoretical physics. Arguing information is more fundamental than matter, and the simple observation that we are ourselves increasingly building computational simulations of physical systems at ever larger scales. The arguments against include the extraordinary computational resources required for a universe-scale simulation at observed fidelity, the explanatory circularity of invoking a simulator to explain fine-tuning, the absence of any confirmed empirical signature distinguishing simulated from non-simulated reality, and the fundamental philosophical difficulty of even articulating what the distinction would mean if discovered. What no credible AI system, including any currently available large language model, has done or could do is provide a novel, scientifically verified answer to this question that goes beyond synthesizing these existing arguments, precisely because the question isn't currently answerable by synthesizing existing information. It's answerable, if it's answerable at all, by future experimental physics of a kind not yet developed, by mathematical advances in our understanding of computational complexity and the relationship between information and physics, and potentially by discoveries about the structure of physical reality at scales we haven't yet probed. The honest, accurate, and genuinely interesting position is that the simulation hypothesis is a live, serious, unresolved question engaged with by legitimate scientists and philosophers, carrying specific, falsifiable predictions in at least some formulations, and connected in deep and still being explored ways to fundamental questions in quantum mechanics, information theory, and the philosophy of consciousness. That's already a stranger, more compelling story than any fabricated AI revelation could manufacture, because it's actually true, actually open, and actually being worked on right now.